be looking at exponents and radicals and how those things are related. So looking here at a radical, so this symbol is your radical. The number underneath the radical is the radicand. And this number right here is the index of the radical. So when there is no index there, we assume the person's talking about the square root. But like if we put a 3 there, we know we're now looking for perfect cubes or a cube root. So if we were going to calculate these, just to give you a reminder of what we would say each of these equals to. Square root of 64 is 8. Square root of negative 64 is negative 8. And if someone asked you, you could use plus or minus, you'd say plus or minus 8. But notice, if someone just asks you to calculate the square root of 64, you don't write plus or minus 8. You write 8 because it's already signed. Okay? The plus or minus comes in when we put radicals into equations that we're solving. But if we're just calculating the answer to someone else's question, we use the sign that's given to us. Okay? So the cube root of a negative is possible to find without imaginary numbers. It's negative 3. Here, the fourth root of 16. Remember, that means you're looking for something to the fourth power, another 4 of the same factors, which here would be 2. Negative because of the negative in front. And here it wouldn't be negative 2, because negative 2 raised to the fourth power would still be positive 16. So right now this is undefined or doesn't have a solution for us. We're not going to get into imaginary numbers with things like fourth roots. They're a little different, and we don't have to go that deep in that area right now. All right, but there's a small problem with x. So let's say I asked you, what is the square root of x squared? You would most likely say x. But that means if I plug in a number like negative 3 for x, and I say, what's the square root of negative 3 squared? You're saying the answer is negative 3. And that is not correct. Okay, the answer would actually be positive 3. So to guarantee this doesn't happen, that someone doesn't get this negative value just because x is negative right there, we would have to put absolute value bars around this so we get the correct answer of 3. So, x to the 6th, we're going to get x. But we're going to put those absolute value bars around it so that nobody accidentally gets that negative. Okay? Here, we have two factors multiplying together. The fourth root of 16 is 2. The fourth root of this quantity, that's to the 12th power. Okay? So remember, there are 12 of these factors, and we're looking for groups of 4. We're going to find 3 groups of 4. So that means this is going to be x plus 3 to the third. This needs to be in absolute value bars. Again, because even if it turned out negative in here, being to the 12th power, it would be positive, we have to be careful of that. So here, the 6th root of something to the 6th power is just going to be that value. And here, we'd want absolute value bars around the x. Now, I wouldn't need them around the y, not because I'm changing the rules, but because the y value here is squared, which means this quantity will never turn out to be negative, because if there was a negative plugged in for y, you would square it and it would still be positive. All right, so if we simplify these, okay, so square root of x to the 8th is x to the 4th. No absolute value here is for 2 reasons. X is to the 4th power, so that will make it positive, and we're including both the plus and the minus. For part B, we're going to have a negative, and then we're going to have a squared plus 1 squared. Okay? So 2 reasons, again, that we're not putting absolute value bars around here, and it's not because of the negative. We would still have to put absolute value bars around the part with a. But a is being squared, so it's guaranteed positive, and the whole quantity is being squared, so it's guaranteed positive. In part C, the 5th root of 32 is 2. And then we'd get x squared and y cubed. I'm not going to put absolute value bars around anything here because I wasn't taking a radical with an even index. Okay? And then for part D, the square root of negative 16, if we're allowed to use imaginary numbers, we'd say 4i. And if not, if we would only work with the real numbers, we'd say that there's no real value. All right, so you can go ahead and try these and bring these back to class with you for the next time we're meeting and talking about this. All right, so here we go again. So for part A, I need that to be positive, and there's no exponents already there guaranteeing that will happen. We already looked at one like B in the previous example where X would need absolute value bars. And in C, we're going to have 3 minus y squared cubed. Okay. This quantity could be negative because this 3 is subtracting the y squared, so we're just going to go ahead and make sure that it's positive. And then you can try these and bring these into class, especially that part A, so we can talk about that. And that's it for 6.1. So 6.1 is just simplifying radicals. But we are also looking here at section 6.2. All right, so now we're going to look at what if they're written in a format of multiplication and division. Oh, and it looks like I already have this from previous. Not good. Okay, so when we multiply, it's like multiplying everything that's under the radical as long as these indices match, the indexes, see? And then when we divide, the same idea. So we're going to use that to help us manipulate. So like in example 1, rather than actually multiply together 125 and 405, break down what those things are equal to. So like 125 down to be 25 times 5, so 5 times 5 times 5. So I'm going to think of this as being the fourth root of 5 times 5 times 5. And then 405, let's see, breaks down to 5 times 81, 9 and 9, and all these factors of 3. So this is going to really be a factor of 5 and 3 times 3 times 3 times 3. And remember, the properties of multiplication say since these indexes match on these radicals, this is really like having all of these factors underneath the same radical. So this is a fourth root, so I'm looking for perfect quartics for groups of 4 factors. So there's a group and there's a group with nothing left over. So 5 to the 4th, when you take the fourth root of that, you'll just get 5. And 3 to the 4th, when you take the fourth root of that, you'll just get 3. So my answer would be 15. Okay? So the goal is to use this to help you manipulate things so that you don't have to work as hard some other ways. All right, so when we look at these next examples, okay, so the cube root of 135x to the thing I'm going to do is break down 5. So 5 goes in there, 27, and then that's 9 and 3. So I'm looking for perfect cubes. So like there's a group of 3 factors. So 3 to the 3rd, when you take the cube root of that, it would be 3. There's only one factor of 5. So that's going to stay inside the cube root. And remember, x to the 5th means there's 5 factors of x. So 3 of those factors will make an x on the outside of the radical. And then there will be 2 factors left inside the radical, and that's the best that I could do. Okay. And then looking at part B, again, I don't really want to multiply 48 and 50 together, so I'm going to go ahead and break this down. Okay, so there's a perfect square. 50 is 5 times 10. 5 times 2, there's a perfect square. I can look at the factor of 2 and 3 and see if they make another perfect square, but in this case they don't. So outside the radical, I'll have a factor of 4 and a factor of 5. Inside the radical, a factor of 3 and a factor of 2. And then dealing with the x's. So this is x to the 5th and x squared. So I have 7 x's total. Okay? Underneath the radical, I have x to the 7th, and I'm taking the square root of that. So there are going to be, as far as groups of 2, there's going to be 3 of them. That will come out, and there will be 1 left over. And then for y's, I have y squared, and y to the 4th is y to the 6th. So if I think about the square root of that, it's y cubed. So my final answer is going to be 20 x cubed, y cubed, square root of 6x. Okay? And I would put absolute values of ours around the y because in both the cases underneath the radical, it had an even power, so it wouldn't look like it was negative. But then here it could be negative, and we know that's not okay. Now the x I wouldn't worry about because, look, there's still a single value of x underneath the radical because of this odd power here, which means if it was negative originally, you wouldn't have a solution, so you wouldn't have to worry about that. So this would be the best way for me to write my final answer. All right, for division, we can do them together or separate. So when I look at this, it's worth thinking if 7, because I can think about it like this too. So if 7 goes into 189 and x squared goes into x to the 7th, this is going to help me simplify. So 7 does go into 189. It goes in, let's see, 27 times. And then x squared into x to the 7th is x to the 5th. So now I have this. So the cube root of 27 is 3. Cube root of x to the 5th is x with x squared factors left inside the radical. So I have something similar in the next problem. When I simplify it, 4 and 32 have common factors, so I'm left with an 8. And 8 has a cube root, and in the numerator, so does x to the 4th. So now I'll start separating it and thinking about what's happening in the numerator versus what's happening in the denominator. And when I simplify this, I'll get x times the cube root of x over 2z times the cube root of y. Radicals are fine, but we normally don't keep radicals in our denominator because we want it rationalized. Now in this case, I need to multiply the cube root of y squared. Because remember, this is not like square roots that you learned in algebra and you're like, oh, I just multiply it by the same thing. You need to make a perfect cube. So 3 factors of y. So I only had 1 factor. I had to multiply by 2 more, and whatever I multiply by in the denominator, I need to do the same in the numerator. Okay? So I'm going to end up with 3x. Oh, sorry. Not 3x, just x. All right, so x times the cube root of xy squared over, and remember, these are going to multiply together to make the cube root of y cubed, which is just going to be y. So in the bottom, I'm going to have 2yz, and that will be the simplified form. So we should be able to work with things like this.